Hi everyone, I am Soumya Sawaran, a third year IT of Data Science and AI department, and today I am going to demonstrate the course project of Big Data Lab. So the problem statement was as follows: energy theft detection in utility companies. So the idea was that many companies were having a time series type of data, and based upon the consumption is the main factor here, and some other parameters like temperature, external temperature, we need to detect the anomalous consumption behavior in the electricity, like the graph goes abruptly high or low. We need to detect that. But for the first thing which we lack here is the enormous amount of data. So first we need to create our synthetic data set, and based upon that data set, the idea is to train a ML or a DL model, and we will fit our model, and we can save that model for the future use. Now, in real time scenario, we need to simulate those scenarios. So in real time, we will use Kafka for real time data processing. We will generate a random data, and based upon our previous experience with the ML model and the synthetic data set, we will classify it in the real time, and at last we will plot it. So this was the main idea behind the project. So this is the objective. As you can actually read the objective. So here it goes. So this is the main column. I'm generating a relational data set in the pandas data frame. So customer ID is the unique customer ID of the company, of the consumer, and timestamp is the x-axis level because it is a time series data. And so you can actually see the parameters. Now, now after that, this code is the main dataset generating code based upon the random sampling from the normal distribution, and with the anomaly, we are creating the dataset. See, dataset generated and saved as energy theft data.txt. Now we can do some data visualization also based upon the generated dataset. So as you can see that this is a very messy kind of data because we have a very large amount of data here. But you can see that those red dots are the anomalies, and you can see that the consumption is high. We can do some other type of plotting also, and see this is the consumption versus temperature. As you can see that the anomaly indicator is high for high consumptions. So any clustering like algorithm or any classical ML algorithm is good enough to detect. As you can see the blue clusters here, the blue clusters are normal. So now, and this is the distribution of the energy consumption, and it resembles like a normal distribution. You can see because we are generating from a normal distribution, and other kind of plots too. Now, what are the suggested ML algorithms? Isolation forest, one class SVM, random forest. Random forest is simple to interpret, uh, and autoencoders are neural network, but neural network will decrease our latency in Kafka. And also XGBoost is a, and we will see that XGBoost performs outperforms the other ML models. Now, some other visualizations for company, some random set of companies. And here we can conclude that the most of the companies exhibit a similar kind of trend. See the different colors, but the trend is similar. So this motivates us to fit a ML model over all the customers. The temperature versus consumption again. And these are the peak hours of consumption, like from 4 to 9 and from 16 to 21. These are the peak hours of consumption in a company. Also, we plotted the correlation between the different columns. See, this is a very important plot. The anomalous data is having an average consumption around 2.5, and a normal is having the consumption. This is a scaled version of the data. You can see the difference. You can clearly see the difference between the average of the anomalous consumption and the normal consumption. Now, this is a plot for a unique customer ID 3. I entered 3 here and the plot is generated. Now, this is the correlation matrix of not between the columns but between the customers, between different customers, multiple time series. I wanted to check that all the time series are coherent or consistent. For that, it is very important to plot a correlation matrix. And the pattern here is that it is correlated with a more or less same amount of value. Let's say for customer 332, see, it is correlated with 0.33, 0.3, 0.3, more or less it is same related to other time series, so it motivates us further to train our ml model. So now I am training one class svm and isolation forest. See, the accuracy of random forest is 96, and of xgboost also it is 96. And wait a minute for, so first for the one class svm it is 92%, and for isolation forest it is 0.88. Now, for random forest and XGBoost, it is 96 for both. But we will choose XGBoost classifiers because the XGBoost is suited to gradient boosting techniques are suited to much complex datasets. It was a close call, but we are choosing XGBoost here due to its high accuracy and versatile features. Autoencoders we are not using here because neural networks will take a very long time to train, and after that also it can decrease the throughput due to the heavy libraries. Because the ML algorithm is well suited for this kind of data analysis here also. Now this is the producer script. Once I will start the Kafka server. Now my model is trained. What is the name of the model? It is XGB model. We will use it further. So I contrasted different ML algorithms and now I chose XGBoost for further classification. Now this is the producer script. So let me explain you the producer script. It will run in the backend because in the notebook we cannot run two scripts simultaneously. So this is the data, random data it will generate. It is the same. It is the same data set, a row of that data set, that synthetic data set which I created earlier, and it will simulate this data and it will send this data to the consumer, and I will consume that data and make a live plot here. So let me demonstrate how. And this is the consumer script. See, producer.produce electricity anomaly, and this will be sent to the consumer. Now the consumer script will parse the data for five different companies I am simulating. So this will pass the data, and now I will process the data from the producer script, and now our XGB model will predict, and that predicted data will be plotted in the plotly. So this is the plotting code and the dashboard creation. I will start the server. So this is the terminal, and I am in the Kafka directory. And now I just need to format my. See, now the Kafka server being is started. Now I just need to run my producer script here in the terminal. See now it started to deliver message. So, like it is continuously running in the terminal, and the message is being delivered to the consumer script. Now we have to consume it. Now for consuming that, see both the scripts are running. Now just I need to run the consumer script and wait for a little amount of time. See the dashboard creation has been started. Now the data will immediately come from the backend through Kafka servers. See, now you can see that the data is coming from the Kafka server. So let us visualize it on the dashboard. This dashboard is in coherence with the script here, and it is updating in real time. See, a new data set comes into the picture, and the consumption is around 6, and it is being flagged as anomalous data. And when the values are low, it is being classified as a normal, not very suspicious level. Red is the suspicious anomalous data, and blue is the normal data. And this is the live temperature plot, corresponding temperature attribute, because these were the main two attributes. Now let us switch the companies, and more or less you can see that there is a similar pattern in all the companies, because we plotted the correlation matrix and it showed that most of the data sets are similar. So let us check for different companies. So in real time it is being plotted, and three scripts are running simultaneously: one the producer, one the consumer, and the Kafka server is also running. Moreover, one thing I would like to discuss that is the latency. So Kafka, your producer and your consumer, you can set the latency here, depending upon the plotting logic. So the one thing here is the callback graph. See, there is a 106 ms delay in updating the plotly graph. So we need to adjust the latency. I tried with very different values of latency, like tune the latency at the back end in the producer and consumer script. So on an average, it runs around 130 milliseconds in updating the child components in the graph. So I set those latency values. See, these are the number of data points, and this is the time taken to update the children component. So I tuned those latency to the value of 200 milliseconds here in the consumer script, and as well as in the producer script. The consumer script, when I tried to adjust it to 80 milliseconds, there was a lag. There was a significant lag in the plotting logic. So we missed those data points. Like the real time processing was not in coherence. So we need to fine tune these latencies as well. So thank you. That was all from my side for the Big Data Lab project using Kafka.